We were on page 24, looking at our affine transformations. Okay, so just remember, an affine transformation was any transformation which was really just a linear transformation. So F is going to be an affine transformation. Applying it to a vector, it's really a linear transformation, but with a translational part allowed as well. So you hit your argument V with the matrix, that's the linear transformation part, and then you translate it by P. So that's it in a formula kind of way, or in a more functional notation, just naming the functions. We can express it like this, and this is going to be our standard form always. So remember, lambda square brackets A represents the linear transformation represented by the matrix A, and TP is translation by the vector P. So translating every point in the plane by P. And so this is function composition here, circle symbol. So it's perform the linear transformation first and then translate. Okay. It's important that you remember that we're agreeing that this order is the standard form, because if they're composed in the opposite order, you know, it's a different one. So that was the affine transformations. Then we spent a bit of time last time discussing the solutions to these exercises. So we'll just quickly review them. So these were exercises 4.1 and 4.2 here were, you know, all the kind of basic constituent, you know, basic operations you want to do with these. So composing two translations, you know, and we found this answer. Composing two translations is to just translate by the sum of the vectors, isn't it? So you translate by one fixed amount and then you translate by another amount. Well, just do it all in one go, just translate by the sum of the vectors. Composing two linear transformations represented by matrices B and A respectively. Well, that's the same as applying the single linear transformation, which is multiplication by the matrix AB. And again, order is important here because the matrix B times A is different from A times B in exactly the same way that the composition of lambda B after lambda A is different from that one, which is lambda A after lambda B. And then there was this one, which is, remember, our standard form was to have the translation after the linear transformation. So, these are our standard form expressions, to have the translation applied after the linear transformation is applied. So here is one in the wrong setup. Here the translation is applied first and then the linear transformation. So if you wanted to push the t through that to get it into the standard form, well, how does that happen? Well, it doesn't just move through it unchanged. The linear transformation comes out the other side unchanged, but now we're translating, and we're translating by A times the vector A, aren't we? Yeah, A times the vector A. So capital A times A. Okay. So then how in general do you compose two affine transformations? Here's one affine transformation, translation vector B, linear transformation B, and there's the other one with A. Well, you're just applying combinations of these rules that we just looked at. First of all, function composition is associative. So all these brackets around the various parts, you can just forget about them, because it doesn't matter how you evaluate this thing in pairs, because function composition is associative. We know that. So we just have to push the TB past the TA to get it beside the other translation. Then we combine the translations and combine the linear transformations lambda. So the linear transformation we'll be talking about is represented by the matrix AB, and the translation part will be A plus matrix A times vector B. Okay. And then the inverse Well, the inverse of a composition we know is the composition of the inverses, but in the opposite order. And then that brought us to the expression, we're going to have the linear transformation represented by A inverse. The inverse of a transformation by the vector A is to simply translate by the vector minus A. And then to push that past that one, it's going to be translation by minus A inverse times A. Okay, so that'll be that composition. So that's what we discussed last time, really. Now, this is going to become much more concrete because in a moment we're going to end up talking about, well, some other kinds of transformations called isometries, but then we're going to be really making things specific and talking about reflections and rotations and, you know, the actual kind of transformations that we're going to be using. Okay. So the point of knowing all these rules, or what knowing all these rules allows you to do, is then if we have any bunch of affine transformations, Fi, and if we compose them, F1 after F2, after et cetera, any composition of them, using these various rules, we'll be able to negotiate the whole thing into a standard form representation. So finding the linear transformation part of the whole composition and the translation part of the whole composition. Just by kind of basically lining them all up like this and bringing all the translation t's through all the matrices out to the front. And then it's just translation by the sum of the resulting vectors multiplied by the linear transformation represented by the product of all those matrices there, just as it was in the case for the two affine transformations there in that exercise 1. Okay, but let's do an actual calculation then, make it a bit more concrete. Okay, so we're going to talk about this affine transformation here. So this is exercise 4.3. So here we're talking about F is translation by P after you perform the linear transformation represented by the matrix A. And we're talking about a specific vector P here, which is coordinates 1, -1, and a specific matrix here, which is this one. And can we attach a meaning to, let's think about, or just investigate this and think about what's the meaning of lambda A? What's the geometric version of lambda A? So it's a linear transformation which is represented by multiplying by this matrix. But can you give a geometric description of that in terms of lines and angles, or, you know, something geometric, not just algebraic like a matrix there? Well, if you think of drawing a quick sketch of the plane, remember, linear transformations are determined by what they do to the basis vectors. All you need to know in order to talk about the linear transformation, all you need to know is what it does to the two basis vectors. So our basis vectors here are I and j. So here's I, here's j. Yeah, and the first column here gives you the image of I. So I moves down to this vector here. So this is A times I. Is this red vector pointing down. And the vector, the j vector, goes to the vector with coordinates 1, 0. So that's just the vector I, isn't it? Well, it's kind of hard to superimpose my red arrow. So we have I and j here. And then they go to, when you perform the linear transformation lambda I, they go to the vector pointing down here and pointing across. So AI and AJ. So what is that geometrically? How do you take these two vectors here and send them to those? Well, you can see it's rotation. My thumb is I, my finger is J. To get it into that configuration, I have to rotate anti-clockwise by 90 degrees. Okay? So geometrically, lambda A is rotation by pi over 2 clockwise. Now, we'll be much more systematic about this later this morning when we'll describe in detail, how to pass from the algebraic representation of a transformation to being able to describe what it is geometrically. Okay, so we'll do this in a more precise way. But so what are some of the things that you're being asked to do in exercise 4.3 is, well, find the standard form representations for f squared, f cubed, say. So f squared, which means f composed with f. F cubed would be f composed with f composed with f. Okay. So that's this translation by p after multiplication by a, after translation by p, after multiplication by a. So using the results of the previous exercises, we know that we can pull this middle translation through that matrix here. And it will become translation by a times p. And then the two linear transformations composed is the same as the linear transformation represented by a squared. Okay, so we can work out these the extra parts we need here. The matrix A times the vector P, which is 0, 1, minus 1, 0 times 1 minus 1. Remember, when we're applying a transformation by multiplying by the matrix, we're always writing our vectors as column vectors. That was the convention we agreed upon. Okay. You can do it representing them as row vectors, but then you have to put the vector on the left, the matrix on the right, and it's the transpose of this matrix that is used. So what do we get here? We're going to get a minus 1 up here and a minus 1 down there. So that's the vector AP. So P plus AP is going to be this plus this, so it's going to be 0 minus 2. And the matrix A squared, well, it's going to be this matrix squared. Well, there's two ways we could arrive at that matrix squared, let's say. You could just multiply them out. Let's do that first. So when you multiply it out, you're going to get minus 1 here, 0 here, 0 there, and minus 1 there. Now, is that right? Can you verify that any other way? Well, if you think about it, think about the geometric picture. The linear transformation represented by multiplication by a, remember we said was rotation by pi over 2 in the clockwise direction. So the linear transformation represented by a squared, well, it'll just be, or the linear transformation, which is the composition of those two, will be rotating by pi over 2 clockwise and then rotating by another pi over 2 clockwise. So if you think about the destinations of the basis vectors I and j under rotating by pi degrees in the clockwise direction, doing 2 pi over 2 rotations, the vector I will swing round to minus I. You can see that because the first column of this has coordinates minus 1, 0. They're the components of the vector minus I. And similarly, the vector j will swing all the way around to minus j. pointing down. And that second column is exactly is the components of the vector minus j, 0, minus 1. Okay. So this is verified by the fact that the columns minus 1, 0, 0, minus 1, these columns are the vectors minus I and minus j, respectively. Which are the images of I and j under rotation by pi. Clockwise, or it turns out that's the same as rotating by pi, anti-clockwise, but in the spirit of what we're talking about rotating by pi over 2 clockwise twice, so we'll say rotation by pi clockwise. Okay. So we could finally then say that the standard form of f squared then is f squared equal to translation by this vector 0, minus 2, followed by the linear transformation represented by the matrix minus 1, 0, 0, minus 1. Because I'm talking about doing pi over 2 twice, yeah. Yeah. Because we're working out f squared, or I was talking about the linear transformation represented by the matrix A squared, which is doing the linear transformation represented by A twice, composing it with itself, yeah. Yeah. Now, geometrically, we could say, what is this f? Well, so f is a translation part and a linear transformation part. The linear transformation part we've seen is rotation by pi over 2, but then it's followed by a translation part. So geometrically, what is f? Well, if you're translating by the vector p minus, 1 minus 1. If you could imagine zooming out from the plane, if you zoomed out to like a million miles away from the plane, translation by the vector 1 minus 1, you wouldn't notice it. It would become insignificant. It may as well not be there if you zoomed out of the plane, because you'd only be talking about shifting everything a tiny bit from a view from very, very far away. So from approximately the transformation f is really just rotation by pi over 2. And then there's a tiny little correction. So essentially it is just rotation by pi over 2. But that tiny little correction, this correction here means that it's not rotation by pi over 2 around the origin, but it's going to be rotation by pi over 2 around some other point. Okay. So it is rotation. So it's still rotation by the same amount, but about or around a point other than the origin. So a question naturally arises, well, what point? What is the center of rotation? Well, that's a question we're going to answer at the end of the chapter. So we need to have a more thorough we need some kind of a systematic thing that will allow us to take transformations represented in standard form like this. So it's some kind of rotation and then a little shift. So that's essentially going to be that kind of rotation, but around what point? Okay, how can you figure out the center of rotation from just that description there? Okay, so we'll answer this. We'll answer this later. Answer this soon. Okay, is that okay? Any questions at this point? So, well, there's a little bit of a discussion paragraph there at the bottom of page 24 about affine transformations. Because they're made up of linear transformations and then a translation, linear transformations always send lines to lines. If you take any line in the plane, apply a linear transformation to the whole plane, that line will move to another line. Yeah. It might stay the same line. If your linear transformation is rotation by pi half a turn around the origin and your line goes to the origin, then when you rotate the whole line, it's still going to look like the same line. So maybe the line might be fixed, but in general, any line will get sent by linear transformation to another line. And because affine transformations are just compositions of a translation part with the linear transformation part, translations also have that property that they send lines to lines. So you got a line, you're just shifting the whole thing by some fixed amount, so it'll still be a line. So they're good in that way. They preserve geometric structures of lines, and hence they'll send kind of squares to other four-sided figures or triangles to other three-sided figures, etc. But what they don't necessarily do is they don't necessarily preserve distances between points or angles between lines. We really do want to restrict we want to try and restrict our discussion to linear transformations that do preserve lengths or do preserve distances, because we're going to use them. Remember, we've talked about how we're going to use these in constructing a three-dimensional virtual environment. We're going to take some kind of basic building block entities and use those to populate our environment, to take various copies of those, and by translating them in various directions, rotating them, maybe scaling them up, scaling them down, we want to do these kind of rigid transformations with them, move them around like that. So the appropriate family of transformations like that are ones called isometries. So isometry is the word, I don't know if it's Greek or Roman, Greek or Latin, I'm not sure, but it's isometric. So iso means the same, metric means distance. Is that Greek or Latin? I don't know, it's one of those two, I'm not quite sure. One of those old languages. Isometric, so an isometry is something that preserves distance. Metric meaning notion of distance. So something that preserves distance. So it's going to be a mapping, I've called it up there, phi, a mapping of the plane phi, which preserves the distance between points. So the distance, or the magnitude of the vector phi of x minus phi of y, that's the vector that points from phi of y to phi of x. We want that to be the same as the magnitude of the vector pointing from y to x. Okay, so the distance between, well, you can say the distance between points or the distance of this vector from phi of y to phi of x, we want that to be the same as the distance of the vector from y to x. Now that's quite a heavy restriction, okay? That restricts the possibility, amongst all the functions from the plane to the plane, that's quite a heavy restriction. And it has consequences. And one of those, or a couple of those, is that it also now has to preserve the dot product. Okay. And also now it has to preserve angles between vectors. Okay. So these isometries we're talking about, they fix the dot product, they preserve the dot product. So the dot product between 5x and 5y has to be the same as the dot product between x and y. And they're also now going to preserve the angle between vectors. Okay. That example we looked at of the rotations, that's an example of an isometry we'll see soon. But you can see that it preserves the angle. These vectors I and j, although they move around, their images are still at the angle between the images is the same as the angle between them at the start. Okay. And that's true of any kind of rotation. If you take two vectors at a certain angle and you rotate the whole plane, they're still going to be at the same angle. The rotation isn't going to change the angle. And isometries also fits well with composition and inverses. If you take any two isometries and compose them, if you run one, apply one after the other, well, if you think about it, that's still going to be an isometry because you're performing a composition of two functions. The first function preserves distances. The second function preserves distances. So overall, you preserve distances and then you preserve them again. So overall, you've preserved the distances. You haven't stretched things at all. Okay. And similarly with inverses, if you have some procedure which moves the plane, but it preserves distances, if you perform it backwards, perform the inverse of it, that's still going to have that same property, that it preserves distances. Okay. So more just to give perhaps to formalize that argument, maybe do a little proof for theorem 4.3. So if we let f and g be isometries, so what does that mean? That means for every pair of vectors in the plane x, y, it means the norm of f of x minus f of y is the same as x minus y, and it also means the norm of g of x minus g of y is the same as x minus y. These are norms of vectors we're talking about here. So what happens when you compose these two isometries? When you run them together. So now we consider the absolute value of f after g applied to some vector x minus f after g applied to some vector y. So we'll let x and y be in the plane, and we'll investigate this difference. What we want to say is we want to be able to argue that this distance is equal to the distance between x and y. And it's just a matter of applying the definition of composition. Well, what is composition? It's just f of g of x and f of g of y. Now the x and y are buried in there, so you just want to lift off the f and the g in a couple of stages. Now the f is on the outside, so we can lift that off first. Here we have an isometry f applied to two arguments, and we're looking at the distance between the images. But f is an isometry, so this must be the same as the distance between g of x and g of y. So that's true since f is an isometry. So if you like, we're applying this property here, but g of x in the place of x and g of y in the place of y. Because these properties are true for every x and y. Okay, so our vector g of x can be one of those vectors, and our vector g of y can be the other one. And then you're just looking at two images of g and the distance between them, so that has to be the same as the distance between the arguments x and y, because g is in isometry. So overall that equation is saying the distance between the images of f and g, the distance between the images of f after g is the same as the distance between the arguments. So that's saying that f after g is an isometry. Okay, and you can give a similar argument for the inverses. So for inverses, we can give ourselves 2 points x and y in the plane, and we can say, suppose that f inverse of x is equal to s, say, and f inverse of y is equal to t. We need the inverse function to exist for this, of course. But then, since f is an isometry, we know that f, the distance between the images of s and t, is the same as the distance between s and t. That's because f is an isometry. But then you just rewrite these things in terms of x and y. You see the distance between s and t, well, s is f inverse of x, and t is f inverse of y. And so the distance between them is the same as the distance between f of s and f of t. But what is f of s? F of s is just x, because s is the f inverse of x, and f of t is just y. So for any pair of vectors x and y in the plane, the images under f inverse, the distance between those images is the same as the distance between x and y. So f inverse is an isometry. Okay, any questions or queries about that? Okay, then, so that's isometries. So we've gone from linear transformations, we've gone to affine transformations, but now we're specializing to these things called isometries, and the condition is they must preserve distances, which general linear transformations don't necessarily. So can we, this next section, section 4.5, is an algebraic characterization of isometries. How does that restriction about preserving distances, how does that feed through to the format of the standard form of an isometry? What conditions does it place on those? Well, first of all, we need to record the fact that isometries are affine transformations. So every isometry can be put into this form here. Okay, so that's lemma 4.4. I might prove that at a later point. But these isometries are linear transformations, and they fix distances, and they preserve distances, and they preserve angles. So if you think about what an isometry does to the basis vectors I and j, the basis vectors I and j have the property that they both have length 1 and that they're at right angles to another. So if you apply an isometry to them, they're still going to both have length 1, and they're still going to be at right angles to one another. Now, being at right angles to one another, you can express that in terms of the dot product. Two vectors are at right angles to one another if their dot product is 0. Okay. So the consequence of that is that the matrix that represents an isometry, the matrix that represents the translation, the linear transformational part of a isometry, has to be what's known as orthogonal. So orthogonal, as a term applied to matrices, what it means is that the dot product of any two different columns with one another is 0. So any two different columns are representing perpendicular vectors, and the dot product of any column with itself is 1. So the columns of an orthogonal matrix are representing unit vectors. So it kind of means that if you have an n by n orthogonal matrix, the columns will be a basis for the n-dimensional vector space, because they'll all be of unit length, and they'll all be pairwise perpendicular to each other. Yeah, so they'll form the basis. So that gives us what's known as this algebraic characterization of isometries. Every isometry is a linear transformation, is an affine transformation, so it has a standard form, and its standard form will be of a special type, and that special type is where the matrix A will be an orthogonal matrix. Okay, so it tells you a lot about the matrix of an isometry. Okay. That's the algebraic characterization of isometries. So later on this morning, we're going to start making things a lot more concrete. We're going to start talking about these in a lot more geometric way, because that's really where we want to get to for the purposes of this course. So we'll start with Theorem 4.6 when I see you again in an hour, and that kind of lists all the different geometric types of isometry that there are, all the different translations, rotations, and reflections, and so on. Okay, so we'll have a good examination of that starting at 11. Okay.